which is the that is the output file for this import cats data. So if you had a problem, if you're running 2020 and you had this problem, this is the file that you can find in the day 2 materials, workshop materials today, and that will allow you to run the scripts that Will's going to go through later on. And if I see that other error that just popped up for that, if you're having an undefined function errors, are usually a path issue. So make sure to go back through and add in all of the folders to your path. Cool. With that, we'll keep hold of those errors. You can keep playing with this for a little bit if you want. We'll keep hold of those errors, keep thinking about it, keep trying it, try to get this file off, get that ready to load up so we can be ready for Will's. But I want to turn it over to Jeremy to kind of give us an introduction to some of the other uses of biologging stuff. And we'll do that for a few minutes, and we'll come back to helping with these errors. So keep thinking about this, but also I want to show Jeremy's stuff because he's got some awesome work going on. So Jeremy Goldbogen was my PhD advisor, Will's current PhD advisor, was one of the people who started working with cats with me and Ari Friedlander and John Kalmakidis in 2014 or 2013 even, and really started to kind of think about like, well, what else can we do to like kind of get more information about these animals? What are some of the research questions we have that we can like really answer with some of these video and data integrated tags? And so he's really kind of pushed the field in that regard. So we'll turn it over to him, and then we'll come back and answer some of these questions you guys have, which are all awesome. So thanks for working on that, guys.
Awesome, thanks, Dave. Special thanks to Dave and Will for putting this workshop on. Thank you everyone for participating. It's great to see the community to come together with a common goal and objective here. I thought I'd give a short and sweet little presentation here that will complement what Ari showed yesterday about sort of putting in context the what we're doing here with these CATS tags and sort of the greater evolution of biologging technology. And it's sort of this growing trend of what I like to call bringing some of the traditional laboratory techniques to the open ocean, or to it would also apply to terrestrial environments as well, of course. But I like to think about it that way. It's you know, some of these animals we obviously can't have in captivity, and from my perspective, I think we can learn a lot by basically advancing these tag technologies and understanding how animals work in their natural environment. So thinking about sort of first this half century of work that has come before where we are now, and then near the end of the talk, I'll talk a little bit about sort of the next half century that the people in this room will define a lot more than I will. I think Ari touched on this just briefly here. Really, the biologging revolution started with Jerry Koyman and the specialization of a custom-made kitchen timer with a pressure transducer that basically etched out the dive profile of a Weddell seal on a smoked glass disc. And this is some of the pictures that Jerry was able to give me about his experiences with this technology. And because there was a 60-minute kitchen timer, Jerry had to reacquire the device every 60 minutes to reset the time on this. So even though you may be plowing through a lot of difficulty and some of the data analysis, just think about sort of where the field has come from in the past 50 years or so. And so you can see this over here, some of the components of that very original time depth recorder. This is also this is a table from a review by Jerry Koyman that shows some of the other firsts in this the evolution of this technology. So here's that first TDR here. Here's the first heart rate recorder by Warren Zapol at Harvard in the 80s. And this is really relevant to what we're doing here, the first CritterCam deployments in the early 90s. And those early CritterCam tags really inspired what we wanted to do in collaboration with cats, and sort of making them a little more functional for answering some organismal biology questions. Okay, so moving ahead from the 60s, a couple of decades later, this is some work done by Paul Ponganis, sort of in this the tag space of physiology. So again, bringing the physiological lab to the open ocean in the form of backpack recorders. So microcomputer processors, and basically combining those with medical devices that can measure things such as temperature, heart rate, and in the last decade or so, also things like gas management in the blood or even in tissues. If there's any Gen Xers in the room here, they'll notice this cassette tape. There was some heart rate data that was originally recorded at proprietary, which is funny enough, onto cassette tapes. And so in the last decade or two, this is some work from Paul Ponganis's lab once again, his students Jessica Mir, Cassandra. These are some of the really amazing physiological sampling devices. You can see a blood sampler here. So obviously these are a little more invasive, so you really need good defined questions to really justify these ethically. They can be done relatively non-invasively when they're done with the proper procedures, of course. Okay, so just some stepping forward into some of the acoustic tag technologies. If I had to point to one tag that has really defined cetacean biology in the last couple of decades, absolutely was the D tag, developed by Mark Johnson. You can see over here on the right, in collaboration with Peter Tyak. It was not the only acoustic tag back in the day. You can see a very young Peter Madsen here with his acoustic tag. And I believe, if I have this right, I think this was an acoustic tag that Peter designed, or this may have been one of the very earliest D tags. I need to ask Peter about that. But this really revolutionized cetacean biology. So it provided a lot of the acoustic environment, as well as acoustic sounds that cetaceans make, as well as the amazing diving behaviors that we still continue to realize today, especially considering beaked whales diving for hours or more. Okay, so this is sort of a just a composite figure here with, these are the evolution of the D tags in the upper left here. So from the late 90s all the way to today. This is version 1, version 2, version 3, and version 4. I need to fix the date here. I forget exactly when version 4 came online. But you can see the perpetual miniaturization of these tags, which is a good thing. The smaller the tag, the less drag. That means you can apply that to smaller and smaller species. And that's a trend, of course, we're seeing with the biologging revolution: smaller tags, cheaper devices, more battery time, so on and so forth. Speaking of small tags, Little Leonardo is probably the best manufacturer in terms of really, really small devices. And they've been deployed on penguins, turtles, and fishes. This is the tag that I did my PhD thesis on, using data from the bioacoustic probe, which later became the Acuson, sort of in the mid 2000s. Before the CritterCam, I think one of the first video camera multi-sensor data integration suites was by Randy Davis, Terry Williams, and others. And they deployed these on Weddell seals in the Antarctic. This was really handy because you can have an isolated dive hole experimental design where you deploy the tags, you can reacquire. That isolated dive hole, of course, is what you saw with Jerry Koyman with that very first TDR. This is the evolution of the CritterCam from the late 80s. I mean, look at this monstrosity, much better today, but this is really what inspired us to think about the CATS tags. And we started dreaming this up in the 2013, 2014. Before I get into the CATS tag data, I just want to show what some of the sort of this is late generation CritterCam deployment on a blue whale. John Francis, John Kalmakidis, and colleagues, and some pretty amazing footage at that time. So this is really what this is the original sketch, as far as I could tell, going all the way back to 2013. We basically said to ourselves, can we make a critter cam that's a little more functional in terms of three-dimensional movement sensing? And how can that sort of push the community uh, and the technology forward in a way that will just basically give us new insights into how these animals work. And so we were experimenting with different camera designs, basically. The number 2 here, we were thinking, oh, maybe we can just have the cameras be positioned like cetacean eyes, which are laterally positioned, of course. But then we thought it might be nice to have overlapping viewpoints of sort of on the more anterior end of the tag here. We also experimented with front and back facing camera designs, which is what you see here in the lower left. Before we actually implemented cameras, we had just regular movement sensing and depth sensing. This is one of the original tags right here. I won't go into some of the details here, but sort of the engineering design process was really part of the challenge here. And it goes beyond just the tag itself. It's also has to do a lot with just getting the tag on and getting the tag back. This is colleague Dr. Allison Stimpert deploying a tag beautifully on this blue whale here. This is when everything goes perfectly. I'll now show you an example of what happens when everything does not go as planned. This is Ari Friedlander deploying one of the earliest CATS tags. Before we had what we call the robot, which is, the robot is basically the device that attaches the tag to the pole. And as you can see here, Ari's in perfect position to tag this humpback whale off the coast of Alaska. The carbon fiber pole is going up, and you can see right here is when the tag is departing from the end of the pole. And even though Ari has this perfect placement here on the tag against the whale, you can see the tag floating off into space. So if you don't have your tag, all the other components that help you get the tag on the whale and tag back, that can really prevent successful data collection. So in that vein, a couple of videos just to set up what I want to talk about next in terms of the engineering design process with respect to tag attachment. I want you to imagine you are the tag, you are the tagger, and this is what you would see. So you're basically holding onto the carbon fiber pole. Blue whale's about to breathe, and that's what it would look like here. So now in this next sequence, now you can imagine you are the tag and you are about to be deployed on the whale. And this is what it would look like. These are all CATS tag sequences here. This is the that number 1 orientation of the camera tag. So basically on the anterior cone of the tag, facing about 45 degrees with respect to one another. So this is an example of one of our design failures where we thought we had a great tag design in terms of the suction cup attachment, but we kept putting the tags on whales and they kept sliding off. This gives you a good appreciation for how long a blue whale is, because it takes quite a bit of time before it slides off the whale. And this was the problem we had. This seemed like a good design because it had this really low profile, so lower drag, big surface area for attachment, but it slid too much. So we wanted a stiffer suction cup, and that resisted that slide much better. So this is part of the fun of sort of tinkering with the engineering design process. And the interesting thing is different suction cup designs might work better on different species, or even the same species in a different environment, different temperature water, or maybe there's a diatom slick on an animal. So you really have to adopt your designs in order to make them successful. So here's an example of a good attachment, just some fun video. Of course, this is the reward of getting the tags back and seeing new things for the first time. This is a remora photobombing our footage. Here's another sequence here. Again, it's that split cam perspective here. We published this recently, Journal of Experimental Biology, just like amazing, because originally we thought, well, remoras just stick to whales. and there's not much exciting there, but they're incredibly agile and they're flying all over these whales, and there's many remoras. So it's like this whole ecosystem that's around a swimming whale that is created by basically the flow shadows of a large object and flow like a whale. So it's just some of the fun. And these little sort of domes erupting out of the whale's body are created by an ectoparasite called Panella. So again, just fun insights into animals that you otherwise wouldn't really have unless you had these animal-born technologies. Here's a look at the lab, again demonstrating sort of that tinkering fun component of this. Again, thinking creatively outside the box and really embracing creativity. Here's one more example of, this is sped up 10 times actual speed. This is from a humpback whale. This is a whale lice. Again, we sort of thought of animals like this just sort of like hunkering down on the surfaces of these whales. What I think you see here are two individuals that are sort of joined here. You're going to see this third individual approach this group. And if you look really closely, you'll see some antennae go up. I don't know, maybe they're communicating here or something. You're going to see some antennae go up in just a moment. It's right there. So maybe that was a threat display, and then you can see the one that got kicked off the island or something like that. So again, sort of these discoveries you wouldn't have, even if you were a great diver and you could have some amazing footage, you really wouldn't see it because you wouldn't have the right frame of reference. Some of the really important data for our group is in terms of mechanics, swimming mechanics, energetics, and actually swimming speed, which we use the high sample rate accelerometer. I'll talk a little bit about that in a second. But actually seeing those feeding events relative to speed changes is really important. And I imagine that sometime in this workshop, you'll talk about how you can derive speed from accelerometer signals. Again, sort of the fun reward is seeing the complex three-dimensional movements of whales. This is 50 times speed for a dive profile of foraging blue whale, sort of this roller coaster-like amazing behaviors. And again, this sort of rich data sets that sort of are, these tags make possible, but also, this is why we get into this business, is to see the amazing things that these animals do. And also it's a social affair as well. So our group, as well as other groups, have put tags on multiple individuals in a group. This is an example of a tagged pair, blue whales. And you can see that just amazing engulfment event that's really characteristic of blue whales, of course, basically doubling in size as they engulf a large volume of water and krill, and take about a minute to filter that volume out. You can see that expanded ventral feeding pouch there. So again, I like to call this sort of digital natural history that these cameras provide, as well as the inertial sensor data that y'all are analyzing. There's really natural history embedded in those patterns and those behaviors as well. This is just a collage of things that we've seen over the years. From killer whales down here, I think Dave showed you that a couple of days ago. Gray whales feeding at high tide on ghost shrimp, humpback whales feeding on anchovies, blue whales feeding on krill, so on and so forth, photobombing our own camera tag footage. And this is sort of the way I think about this process. We have these tags, it gives us these observations, and that allows us to think about biology and ecology in new ways. And we can generate these hypotheses that we can then ask of the data that the tags are generating. And it's sort of this nice feedback loop. And I tell this to a lot of students. Every time we deploy a tag, we sort of learn something new. And by working with groups across the world who are tagging other species, you can put together these really fun comparative studies to not only understand how animals work and interact with their environment, but how they evolve as well. This is just one sort of outside the box thinking that the CATS folks did, is think about this one lens that could sort of give you an almost 360-degree view of the whale's environment. And you can embed this into, you can incorporate this into an Oculus or Google Cardboard or something like that, so you can sort of look around as if you were riding on the back of a whale, and really getting that Umwelt, what is the sensory experience of these whales. So the time scales here, I think later on in the workshop, you'll talk a little bit about some of the different types of tags that might stay on animals for longer. So going from sort of microseconds all the way up to years and decades. There are actual tags that can be implanted, for example, in seals. They're called life history tags. And so they're basically in seals for 10 years or longer. And you know, it's a really long research program to think about, but it's amazing data. So you can really get basically life history data for an entire animal from these tags. And for example, if you had a tag in a fish and it ended up in the stomach of a seal, and then all of a sudden your tag has sort of transferred species, and now you're getting like life history data from another individual. So that's one of the really fun and crazy ways to think about this biologging revolution. So you can see the full time scale here of all the really amazing different applications that these tags provide. Just a shout out for sampling resolution. So you're probably working with data that's sampling possibly up to 500 times a second, or if it's acoustic data, even higher, of course. I once had an engineer say to me, a tag engineer, why would you want to sample movement data for a whale greater than 1 hertz? So that's once a second. This is when I was a graduate student. I was like, because I was working on 1 hertz data for whale movement, and it was very cool. But I really wanted more resolution, and the reason for that, and now we have up to 500, 800 sampling accelerometer sampling per second, and it can enable some amazing discoveries like whale calls, for example. You can actually see the movement of the call registering on the accelerometer, which is very handy when it's a low frequency call. You don't know if it's the whale next to the tag whale that's calling or the whale itself if you had a hydrophone, but if you have an accelerometer, it might give you more greater confidence in that inference. And also we've turned sort of this noise here. You can see the sort of the jiggle in the tag sensor here, and we've actually converted that into a jiggle speedometer, which is really useful for dead reckoning, of course. And sort of returning back to physiology, heart rate. And when you have an animal in captivity, you might be able to put sort of this wetsuit on this dolphin in order to get the electrodes in just the right place to measure heart rate. This is a killer whale at SeaWorld. This is from Denmark, our colleagues in Denmark, where you can have these 2 electrodes like so. We've had some difficulty in this, but some success, just putting 2 electrodes in 2 of the 4 suction cups to measure heart rate of blue whales. And that's some of the sort of the future of where this is going, is more and more physiological measures to go with the behavior as well as the ecology. I just wanted to show you some examples and applications beyond whales or even marine vertebrates. Mark Johnson is at it again, making this really basically a tiny D tag for bats. Just incredible. You can see the backpack tag here on this 27-gram bat, recaptured after 9 days, recorded a lot of amazing acoustic data, echolocation data of bats, as well as movement as well. This is Dr. Sabrina Fawcett, who is a researcher here in Monterey, but has moved to Australia. She innovated in the space of tag attachment to a jellyfish, which is really cool. There's all these different ways. You can have a collar on a jellyfish. You can actually just have medical glues. Basically, you know, what does a jellyfish do? It's actually much cooler than you think. And there's ways that they basically swim against the current, and they can actually register the shear of the water column and can prevent themselves from stranding by basically swimming against the current. So, you know, the whole amazing life of jellyfish revealed by biologging tags. And also, I want to end by saying biologging can lead to other careers that are outside academia that are pretty awesome. An amazing researcher, one of my research heroes that I went to graduate school with, Dr. Jessica Muir. She did her PhD thesis at Scripps Institution of Oceanography in biologging technologies on elephant seals as well as emperor penguins. And of course, she is now a NASA astronaut. So I just wanted to say that people have gone on to run companies using biologging technologies and have had some amazing career trajectories. And also, commercially important as well. A lot of the sensors we're using here in the CATS tags are in cell phones and smartphones. So there's a wide variety of applications and career trajectories as well. So I just want to leave it at that. So hopefully that was just some fun things to think about, break up some of your data analysis, and think about the next half century of biologging. So thanks again to Will and Dave. I'm happy to answer questions, but if you need to stay on time, I'm happy to answer questions via email or otherwise.
Thanks, Jared. That was awesome. There's so much good stuff. We can take a couple questions for now if people have any questions for Jeremy. Otherwise, we'll go back to the data.
And I can't see the chat because I'm sharing my screen. So Dave, if you want to curate the Q&A via chat, if any of the questions come in through the chat.
Right on. Seems people are ready. Oh wait, here we go. What do you do with data that has a low light profile?
Low light profile. So if we get video that's dark, basically?
Yeah, right. Like exactly. Like if it's just dark all the time.
Yeah. Well, I mean, I don't know, David, I don't know if you've talked about it yet, but there is a way to program the CATS tag to stop recording video when the light levels are too low. So there's different ways to deal with this. So turn off the camera when it's too dark, or innovate in the space of better cameras. So low light sensitivity, starlight cameras. So it really depends. It goes back to this engineering design process of, it depends on the question, depends on the species. So if you're studying sperm whales or beaked whales, you might want to have an infrared camera or something like that, or some kind of infrared light that you can illuminate with. So it really depends. I mean, we've been lucky enough to get video data down to, what was it in the Azores, Dave? Was it 300 meters? Maybe?
Yeah, 320 or something. There was still light downwelling from the surface to get a nice profile of the krill patch above it.
Yeah, so that's really fun. If you can work in clear water, I would suggest it for the CATS tags. And there, in contrast to the Azores example, some of the tag deployments on humpbacks in Monterey, if they dive, to 10 or 20 meters, it's already so murky you can't really see much at all. But somehow they're feeding on fish in water that our cameras cannot see. And so that's also very cool, because then it begs the question of how are they finding and feeding successfully on fish like sardines and anchovies in super murky water. So again, that goes back to this amazing feedback loop of these new observations, even though it may not be exciting video data to share, but it gives you this new question of how do whales find fish in murky water, especially humpback whales, which don't apparently have echolocation. So, and then, okay, well, how can we adopt and advance the tag design in order to answer that question? So it's sort of this iterative positive feedback loop that I find really fun, and I hope everyone in this room will find fun as well.
Thanks, Jared. One more question, and then we'll get back to data. It says Suzanne says, I know little Leonardo is making tags with lights. Do you know of any research on the effect that adding lights has on the behavior of seals or penguins?
Oh yeah, great question. Yeah, we always have to be aware of, is the tag technology and our application of the tags to the whales or animals, is it affecting their behavior? And that's a difficult question. When we are tagging whales that are foraging and they go back to foraging based on the tag data. That gives us confidence that we're not affecting their behavior too much. It's also that the tags on our whales are really small relative to their size. So when you get to smaller animals, the tag size does become a factor. So we really need to think about that holistically. In terms of light, that's a good point. You know, and whether it's affecting the tagged animal or the tagged animal's prey, that's a difficult one to answer. And I don't have a good answer, but we should be thinking about that all the time, because if we're affecting the behaviors so substantially that we're not actually capturing natural behaviors, then we've sort of defeated the purpose almost. So we really need to define the questions, make sure we're performing the research ethically and reasonably, and sort of, you know, I don't like to use the word using animals, but that's how university IACUC protocols basically define it as. But when I like to call it a collaboration, when we're collaborating and working with animals, if they allow us to tag them, we want to make sure we're doing it in a way that's minimally invasive and also giving us really important data that's important to the conservation and ecology of the species.
Thanks, Jer. That was awesome. Yeah, Jeremy is available to contact by email, or his website has his contact information. And I don't know if you want to, is it okay if I share your email address right here, Jer?
Sure, yeah, absolutely. Yeah, thanks everyone. Yeah, stay the course, have fun with the data. Yeah, let me know if you have any questions. Thanks again, Dave and Will. Thank you everyone for participating. Stay safe, take care of everybody, I'll see you all soon.
Thanks, Jeremy. That was awesome. It was really cool to just get some new perspectives and just remind us what we're doing out here. So, yeah, I wish we could do the round of applause for Jeremy, but we can't. It's hard to express his sport. But I think I've seen a lot of good smiley faces as you were doing it, Jeremy. So thanks for doing that. We will, on that note, let's get back to like how do we get into this data, and I want to just highlight a cool aspect of what happened in the last interaction with that breakout session. So we had a lot of people kind of come back to me and say like, oh, it's not working, I'm having this error. And I'll share my screen because the great thing that people were able to do is tell me really precisely. So if you ever have to have an error that crops up in your code, the best thing you can do is like screenshot or send me exactly what the error is. The best thing you can do is try to fix it yourself and then send me the updated code. That's the best thing. And then I'll just update it and be like, yes, you fixed it. You fixed this error code. That's fantastic. Let's upload that. And we can even put a little credit in there for you for helping you do this error checking. But short of that, the next best thing is telling me exactly where the error happened. So Teresa and Leah and Tammy in another room there told me that they had an error in version 2020 when they're importing CATS data. They're getting this error at the specific line. So then I was able to go into the code and say like, okay, well, that's happening at this read table line. And then I was like, okay, well, what's happening and why is it only happening in 2020? And so the way I could handle that is then basically one of the functions you can use for error checking in MATLAB, just to kind of show you guys this, is you can go to this function called doc. So whenever you have a function that's breaking down, you can use doc or whatever just to understand more about it. And that opens up this window that tells you what is happening, what that function's all about. And indeed, if I read this window and I read this description, it says, where is it? 2020. So starting in 2020, the read table function reads it differently. It operates differently. Like MATLAB changed the way that this read table function works. It's still basically the same, but it has some new switches in there. And so to kind of make it work in the old way, you have to add in this switch in here that says format auto so that it reads the headers as part of the CSV instead of not reading the headers. So it's just that code's always changing, everything's always changing. Like it can be frustrating, but it can also be awesome because the read table function now is more dynamic in general. It just doesn't work for our old code. So I had to go in there, I changed the old code so that it's gonna work for both of our versions now. So if it does a version check here, and then if the version is less than 2020, it does it the old way. If the version is past 2020, it has this format switch in there. And so we've changed that. I've uploaded that to the GitHub. So now that should work for you guys to be able to operate. Like I said, if you don't have that already, that's okay. You can still find it in the, if you didn't get a chance to run that file, you can find it in the workshop folder, in the workshop materials, in day 2, in the data files. There is this tag 70 mat file. That is the data for what Will is going to do next that you're going to work with. That and this bench test example are the 2 pieces that Will is going to work with to import our data there. Excellent. So with that, actually, we will turn that over to Will. We'll come back. We'll start talking about import, cast data and stuff later. But the point of this calibration exercise, basically, remember, we're taking a step back. We're looking at data after it first comes from a tag. And how do you kind of like see what the data is actually doing and how do these tags operate? We're still kind of thinking about the guts of the tag and what things work on. And then later, after the calibration exercise, we'll come back to thinking about our sample deployment and actually making some using that calibration file to start calibrating our in situ data and going from there and looking at, we'll examine our movie times files a little bit as well. So taking it over to Will for some calibration.
Great. Cool. Thank you, Dave. So it looks like we have a question in the chat about what the figures are that pop up from the import cats data script. We'll go through those in a little bit later on. There's also, I think there was one other error that somebody was getting. So if you would be willing to sort of send that along to Dave, like he's saying, that would be really really helpful. So
Will, I can just answer that question really quickly.
Oh,
we're
sure.
On import cats data. That would be great
let's do
to
it.
look at. Just what are these figures that pop up when you run import cats data? Okay, great. So one of the reasons when you run import cats data, one of the things we do when we get data back from an animal, we run this script immediately. We get the data, we download it. The first thing we do before we redeploy the tag is we run this script. And the reason is because it gives us checks that our data is working. The worst thing that happens is you get a tag back, it was working before, and now something happened to it. And it's like, oh, like the accelerometer crapped out. And then you put it on another animal, and then you have bad data again. So one of the first things we do all the time, and you know, that's rare, but when it happens, it's like it pulls your hair out because you're like, why did I deploy that tag again when it didn't work? So one of the things it does is it just gives you a plot of your data to kind of look at, like, well, okay, is my data okay? In this situation, this is calibration data, so there's no pressure data here. But normally it'll spit out like actually a whole TDR, time depth record of what your tag did. So you can see, like, what did my animal do? When did that tag pop off? What was in general it up to? So that's what everyone wants to know as soon as the tag comes back anyway. So it gives you that information. What is that animal doing? What is that time depth record looking like? And then it just plots your accelerometer and your magnetometer profiles, which are critical sensors, to be able to say, like, okay, am I getting data? Is there any sense that like one of these columns crapped out, or does anything look like, is there like really big spikes in the data? Like things that can happen as tags like wear out over time, or as there's things that would go wrong. So this is just a sense for you to actually just be able to look at your data and as a first run of like, here's a deployment. Do I have data that looks like data? And if I don't, then I can back up and say, like, I don't want to deploy this tag again. I'll deal with those spikes later, but that's what's going on. So it's just, I always run this import cats data as soon as we get a tag back from the field, run this script, it'll spit out this information for you. Great question. Thank you for asking that, what comes from that. Okay, now we have this calibration data. We just spit this out. We're gonna turn this over to Will to talk about what to do with this data. And you can see this is calibration data. It has these nice like flat sections and stuff, which is what Will is going to be talking about and showing. And what we're gonna zoom in, I'm taking a little of his thunder, but one of the things he's gonna talk about is basically creating these sections where you have these really these spinning values to like actually have calibrated to figure out what this tag is actually doing and where it's supposed to be. Okay, that's enough for me.
Yeah. Okay. So I think I'm going to kind of do this in 2 ways. I'm going to talk first about sort of like the tag itself and how you can go about creating your calibration data set. And you know, how do you sort of get your maximal values and do everything there. And then we're going to come back to the code and say, okay, now that we have created our data set with the tag and we've successfully imported it, what are we going to do with this calibrate cats MATLAB script? So to start out, let's start with this short video that essentially, it's on the left-hand side, you're going to see this is the cats tag UI, so the user interface. And there's quite a few shots of this on the wiki. There's actually a sort of small tutorial that goes through like what are the important pieces of it. And if you go to the calibrate cats section, so calibrating the tag, you'll see here's the UI here. And so we're going to kind of be going through live view in this video here. So essentially what you do, you open up the UI here. Can everybody see this? Okay. So you open up the live view. And if you open up the charts, now you see it'll essentially kind of the similar to what sensor kinetics was doing yesterday. It's showing you a live view of the sensors in the tag. And so on the right here, you're going to see the tag itself, and you're going to see what I was doing with that tag. Actually, turn off the audio here. So you're going to see, again, I'm going to turn it over. And so thinking back to the sensor kinetics, what just changed? Well, the big thing that changed, we had our X and Y axes stay the same. They stayed at 0. And our Z axis flipped. So it went from negative 1G to positive 1G. So what we can use, and I can make this video available online, we can use this to sort of check the axis conventions of the tag. So like Dave was saying yesterday, you know, you can open up this live view and really see what the tag is doing by, you know, flipping it around and holding it on all of these different axes. So here we can see we're in the positive X direction. And now we're going to be in the negative X direction because we flipped it over again. And so finally, and maybe the most confusing to figure out sort of like which side is which, we're going to have the y-axis. So here we have that we're on the positive y-axis, the positive y direction. You can also see there, as I flip the tag around, you saw that the magnetometer shifts a little bit too. Because remember, the magnetometer is based on the magnetic field strength of Earth, not just the orientation of the tag. And here we flip it, and now we're in the negative y direction. And then the final little piece I'm gonna do in this video, you're gonna see me performing a behavior that we see our whales doing a lot, which is fluking, swimming, active swimming. So you see I'm gonna kind of hold this tag here in a second, pick it up. You see I'm just gonna kind of move it up and down, back and forth. And you can really see that in both the accelerometer and the gyroscope. So this is something I'm gonna talk about later, and I'll actually probably come back to this video a little bit, that you can use different axes and different inertial sensing units to get a sense for different behaviors. And so, you know, this is the live view of the tag, but it's not necessarily calibrated. So what we need to do is create this calibration data set. So I'm gonna move out of there. And we're actually, if you follow along with the wiki, I have created some small little YouTube videos that sort of go through some of this. But what I wanna do is start off with this Excel sheet. So this Excel sheet is going to be all of the data and essentially all of the metadata that goes along with your small calibration data set to tell the MATLAB code where to look. What time should it be looking at, right? Because you're gonna have the tag on and you're gonna be doing stuff, and you're going to have to walk outside for the magnetometer calibration and walk back inside. So there's going to be a lot of downtime. And so you really want to have a sense for like which chunks of time are important. And so in here, as we open this up, in particular, we have for, so we have the Latin long. We need to know the position of where we are in space, in geographic space. And then down here we have the accelerometer, and over here we have the magnetometer. And so the magnetometer actually, the calibration for the magnetometer also helps to calibrate the accelerometer. But we do like to do them in two different ways. And the accelerometer calibration also helps to calibrate the gyroscope. So we're sort of calibrating them all together. And so what we do, and I'm actually going to, I'll leave this up here and I'm actually going to stop sharing. And then I'm going to move over. So if anybody can see, I'm going to mute myself here. I'm going to unmute myself. Okay. That's terrible. Okay. Can you guys hear me through here?
Yeah, well, that looks good.
Dave, can you hear me?
That sounds good. Well, yeah.
Okay, good. So hello, everyone over there. I'm now on my phone. So if you look through and you see Will Gough's iPhone, that's where I'm coming to you from right now and for the next just few minutes. So what we're going to be doing is creating this small data set. And so the way to do this,
I'll jump in, Will, and just say that as a Zoom thing,
Yeah.
if you guys need to, you can maximize the speaker view, and that would make Will's vote big. So I think it's under the somewhere under the view button, you can have speaker view, and that'll make the speaker under the view button. You can have speaker view, and that'll make the speaker big. So you can see Will's iPhone bigger that way.
Okay. So the way that we want to calibrate the accelerometer and the gyroscope is by having something, a turntable or a lathe we've used before that has a known rotational rate. And we're essentially going to take our tag and we're going to put it on that and let it spin. And we actually use, in our lab here, you see, we use a record player, which is very fun. So I'm actually going to break the record player apart a little bit. I'm going to take the record out of it, hopefully without damaging it. Just going to put it over here. Okay, so now we have our turntable, which is really nice because not only does it turn, but it turns at two separate known rotational rates. So it turns at 33 RPM and at 45 RPM. So in order to create our little data set here, we're going to move back to the Excel sheet, and you can see that it says in there that there are 6 different positions of the tag. And so if you think about it, you know, we have 1 position, 2 positions, 3 positions, 4, and then we have 5 and 6. So we need to calibrate in all 6 of those positions. And so what that means is we need to put this tag on our turntable and rotate in all 6 of those positions. So what we do is we typically, we choose a time and we sort of set our time first to make sure that the clock on our computer is accurate. And then we will put the tag on here and we'll basically start counting 30 seconds. And we put that into these green spaces on our Excel sheet. Sorry, I'm kind of moving back and forth here a little bit. So we're going to put that into the green space on our sheet. And essentially what happens is we'll put it on here and we'll leave it for 30 seconds. And then 30 seconds later, we will start turning. And then this will
go into the next column or the next row down. So the first yellow row below that. And so this is now turning at 33 RPM. And then 30 seconds later after that, we're going to turn it up to 45 RPM. We're going to let it rotate faster. And so once we've done this, so it's going to take, a minute and a half to do one position. Once we're done with that, then we're going to do the next position. So we're going to turn it over. Turn it on. We're going to wait 30 seconds now that it's stable. So we're going to put this time into the green cell. And then again, 30 seconds later, we're going to turn it on to 33 RPM, wait 30 seconds, and then turn it to 45 RPM. And then when we're done with that, again, we'll turn it off. And so for some of the other positions, it gets a little bit weird because again, we're trying to sort of hold this tag in positions that are not the most stable. So a lot of times what we do is we have all of this foam and stuff in the lab that we kind of have these big pieces. You can see we've got chunks of it up there. And so we sort of use this to maintain the position of the tag in some of these weirder positions. So as you can see, we have the official calibration stand. And this is one of our older ones. So this was Platypus edition, which is one of the older types of tags. And so we sort of set this up here. And then if we were trying to get the tag, and I'm not going to do this very well right now, but this is a demonstration. We can sort of mush the tag in here. And if we need, we can put a little extra padding in here. We can maybe put even a little bit more. And you can see I'm going to kind of line it up to make sure that the tag is in the right position. Looks pretty good. And then once again, I'm going to let it sit for 30 seconds. I'm going to note the time. After 30 seconds have passed, I'm going to turn it on. 33 RPM. 30 seconds later, 45 RPM. Now the RPM rate, and Dave, correct me if I'm wrong, the RPM rate doesn't matter, just as long as you have a few different RPM rates with your either, again, turntable or lathe or something similar that allows you to rotate your tag.
Yeah, and that's exactly right. And this is, all of this is just to give context again. This is for the gyroscope, and which CATS tags have gyroscopes, but they're not, it depends if your purposes use gyroscopes or not. And it's really hard to calibrate gyroscopes in situ. So this bench test is kind of the best way to get your gyroscope calibration going on for your gyroscope. So if you have some access to a turntable, you just need two different speeds to a record player or like a lathe or something spins on some kind of wood machine. You can spin those things in different ways, as long as there are two different speeds. And you can call them 33 and 45 RPMs, but we'll actually calculate, as Will show you next, the rotation rates from the magnetometers in the tag as you spin it.
And so what I'm going to do next step here, is the calculation for the magnetometer, which is on the right-hand side of that Excel sheet. And so what we're going to do for this, and what we tend to do, we go outside and we go away from any magnetic interference. So that's why we go outside. It's tough to do that inside. There's computers, there's phones, there's all kinds of stuff. So what we do, we go outside here and we do some sort of basic turning, some slow motion turning of our tag. And you can see this shown in that final magnetometer calibration YouTube video that is on the wiki there. And I'm just going to very, very quickly demonstrate what we mean by that. So again, we have our tag. I am outside here. I'm actually going to very quickly try to find something to hold the phone. That's fine. Okay. I'm gonna set the phone up here. Let me know if you guys can't see that. So can you guys see me now? Dave, can you see me?
Yes, well, yep, we can see you. That's good. It's a good view. You're right in the center of the frame.
Cool. So I'm outside. I'm away from all interference. My phone is technically interference. So if you're outside, we would recommend just, putting your phone 10 feet away or 15 feet away or something. So you have your tag. Now what I'm going to do, and I would typically be turning toward north, but just for this demonstration, we're going to assume that north is in that direction right there. So what I'm going to do is I'm going to take my tag, I'm going to point it toward magnetic north. And so again, as we said yesterday, magnetic north isn't necessarily right at the horizon. Magnetic north, depending on where we are, might be straight down or inclined quite substantially. So what I'm going to do is I'm going to turn my tag and try to find that magnetic north position. And then starting from there, I'm going to start to slowly and very smoothly rotate the tag. And I'm going to do this maybe, anywhere from 4 to 6 times. And I say in the YouTube video that you have to do it in one direction and then rotate back in the other direction. You don't actually have to do that. The goal of this is to find your maximum value for your magnetometer in all of your different axes directions. So essentially, we're just trying to rotate this such that at some point, we are faced directly toward magnetic north. So as you're rotating, if you want to sort of, move a little bit left and right, just to make sure that you're really on that magnetic north position line. All right, so we're going to do this a few times. And once we've done that first axis, what we need to do now is turn and do the other 2 axes. So I just did the x-axis. Now I'm going to turn it, and I'm going to do the next axis here, right, which is going to be essentially rotating the tag like this. Okay, so I'm going to do that a few times. And then the third axis is going to be faced this way. And there I'm going to do again. Actually, I think I might have misspoke. I think this might be the y-axis that I'm doing right now. And we want it to be slow and smooth and as steady as we can make it. Okay. And once we've done that, we have our calibration. We have our magnetometer calibration. And one thing to note here, if you're working with a tag that has a camera, what we recommend is that you perform this magnetometer calibration once with the camera on and once with the camera off. And you can set up the CATS user interface to turn the camera on and off at specific times. So if you're really good, you can set up the camera to turn either on or off in a half an hour, and then you perform all your calibrations, your inside calibrations for your gyroscope and accelerometer, and then your outside magnetometer calibration. And then wait your 10 or 15 minutes, and then go back outside and do it again once the tag has, once the camera has either turned on or off. I'm just going to head back inside now.
And I'll add that, yeah, so this is, will all this would obviously be with once you turned your tag on. And so the data that you just downloaded using your import CATS is data that we used with this tag earlier on when we did the calibration for this tag. So the next steps is we're going to show you like how we actually recorded all that data and what it looks like, and then how do you actually look at your data and see what is going on. Ellen asks, how often do you recalibrate the same tag? And the answer is that we usually just do it once early on. And the reason for that is because we're actually like, this is a good setup and a good like baseline calibration, but your data is going to vary both over time, but also like with temperature and all those things like that. So in your individual deployment, we're actually talking about later today, or maybe it might push it tomorrow morning, but recalibrating your tags in situ using your in situ data. So as long as you have the baseline calibration from the lab, the one time, that's usually sufficient for having good, accurate data moving on from there.
Okay, great question. Yeah. Okay, so I'm back inside now. I've done my calibration. Like Dave said, I had my tag turned on for that whole time. So I come back inside, turn my tag off, and just really quickly, once again, this is where you're going to put in sort of your initial time for each of your rotations for your gyroscope and accelerometer calibration. And a lot of times what will happen is once you put in this first one, it'll automatically populate these next 2 rows, which is nice if you have a turntable or something like that, where you can just automatically click it to change the rate of rotation. And then again, like I said, over here, we have the calibration period for your magnetometer, both camera on and camera off. In this one, you can see that we weren't worried about the camera, so it's the same numbers in either, in both, but for yours, they would potentially be different. And so once we have this, and you have, performed your calibration, you have your data, you've turned it off, you've now downloaded all your data, and you have run the import cats script on that data. So now what you have is you have so you've run your script on here, and you end up with your .map file, which has all of that imported data. So this is the same as a deployment. It's just like a small mini deployment. So,
Will, I'm going to jump in here because a couple more questions related to what you just said that I'm just seeing now. So there's a couple of calibration related questions. One is, all the stuff that Will's doing, do you have to do this calibration in the place that you're going to do the field site? So if you get your tags at home and then you're going to some far-flung field site, do you have to do the calibration there? And the answer is no, you don't have to. You can do it at your home site. The trick is in that bench file that Will showed. I don't know if you can open that back up again, Will, that bench test calibration. If you put in the lat long of the location that you're there, one of the things that it works on is calculating the, it'll calculate the magnetic field in your location. And then whenever, one of the reasons that for whatever your deployment is, it'll recalculate, we have it set up to recalculate your magnetic field in the location that you're at. So it'll always kind of account for that. So one of the reasons, as long as you have this done with the magnetic field in your location, then we can recalibrate that based on the magnetic field in the other location automatically. So you don't have to do that in the geographic location you're at. We had a couple of people saying there's warnings in the new import cats data as you're trying to get this data located. Yeah, I saw that. That's okay. It should end up fine. Another question about how do you find magnetic north? Will said, okay, we want to rotate those tags in the magnetic field so that you're actually rotating through magnetic north so you can get in that maximum value as much as possible. And the answer is it doesn't have to be perfect. So you can use any compass. You can use any kind of compass that is even on your phone has like a basic compass that is going to be off by several degrees usually, but it's okay as long as you're kind of close, because the point is to just kind of increase maximum variation. And so the magnetic field, as Will said, is never going to be exactly 0 degrees flat. It's going to be inclinated. And as you rotate through, you're going to hit that magnetic field, that maximum value. So you do not have to be watching it live as you're looking for those. And then, yes, one more question is, do you have to calibrate every tag, even if they're the same model? And the answer is, that's certainly the best option. Like if you can get away with it probably especially because we're going to do in situ calibrations, but especially if you want to use the gyroscopes at all, it's best to do an individual calibration for each tag.
So and there's one more that just came in too.
And if you have field deployments, can you retroactively calibrate tags? You can, of course you can. That's great. We always recommend doing this right away because because of whatever happens in the field, right? Like the field is the field. So maybe you get 3 good deployments, in the 4th deployment, the tag is lost forever and you never get to calibrate your tag. And so that's always sad. So you can, if you still have your tag, yes, definitely do a calibration now. I think that was it. So
that's all we got. Cool.
Yep.
Awesome. Okay. So you have done your calibration, you've imported your data, you have your mat file, and you have your bench test file here. So what we're going to be creating now is this CATSCAL 70, since it's tag 70, which is the actual calibration file that we're going to use later on in the overall PRH creation process. So we're going to go into MATLAB here, and we're going to open this calibrate cats script. And once we've done that, we're pretty much just going to run through each cell of this script. So I'm going to start with cell 1. So I'm going to run this section. I tend to, and this is just like a small MATLAB thing, I tend to use either run section or run in advance. I don't really use run that often, especially because a lot of these scripts have multiple cells and multiple cells that require you to do things interspersed. So if you ask it to just run the whole thing, it'll run step 2, and then once it's finished, it'll just start on step 3 and then start on step 4 and start on step 5, which you might not want it to do. You might want to take a break in between. So I'm going to just do this as run section. And so it's going to open up and it's going to ask me for the mat file with my accelerometer and gyroscope positions.
And well, I'll just jump in here that this is one people can try to play along at home while they're doing this.
Yes.
We're not going to do a separate breakout session for this. So you should have that data file you just imported, or you have it in the day 2 folder to get this, and you have that bench test file as well. So you should be able to play along at home and see if this works for you.
Yeah, this is going to be pretty quick. So, yeah, it's probably easier if we just go through together. So I'm going to find my tag 70 calibration. So this is your imported .mat file. So I'm going to click on that. And now it's going to ask me for my Excel file with calibration start times, which is that Excel sheet that we were just working with. So I'm going to click on that. So it's going to run a calibration for my accelerometer. And so Dave might have a little more detail on this. I tend to sort of just check this and make sure that nothing looks completely crazy. Main thing to check is that your values are right around 1. If you're getting values that are all the way up at 1.5 or something, averaging, then you might have a little more of an issue. But the actual calibration period here is going to be in this section right here. So like I kind of mentioned a little bit earlier on, you're going to turn your tag on and it's going to sit for a little while as you're figuring out where you're going to go, and you're setting up your turntable and doing all this and that. So you're going to get a lot of these just sort of like dead periods of nothing. Or, maybe you picked the tag up and moved it from this desk to that desk, and so there's going to be a little signal, but not all of everything in here is real data and usable data.
Well, I'll clarify that. So those of you guys who are used to working with accelerometer data kind of know this already. But if it's new to you, the accelerometer, one of the issues with it, right, is it's a magical tool, but it does measure 2 kinds or 3 kinds of acceleration. It measures the static acceleration from gravity. So when the tag's not moving, you get those values that are down there by 1 that Will was just showing. If the tag is moving, then you also have a dynamic acceleration signal added on top of that. And so a lot of the tag tools that Mark Johnson's worked on are ways to help separate those 2 kinds of acceleration. And then there's third acceleration too, which is just noise that can come from the flow noise of the water around the hydrophone. And we'll use that noise as well later on. So when the tag's not moving, it's just the dynamic acceleration, just the static acceleration, that gravity related acceleration that is useful. And so that's what we're trying to calibrate when that tag is totally still there. So that's that.
And this here is your your actual calibration matrix. So this is in each of your axes. So, you know, what you're looking for here is that in each one of these, you basically have two axes that are going to be 0 and one that's going to be either positive 1G or negative 1G. So positive 10 or negative 10. So here we can see we have 9.8333, and then we have pretty much 0, close to 0. And then we have the same, and it's now it's negative 1G. And then we can see that in these next two, now once again we have 1G and negative 1G and then zeros, but now it's in the next axis. And then these final two columns, or these final two rows, excuse me, are in this third axis. Looks like we have a question. Oh, which subfolder has the calibrate cats in the MATLAB methods material?
Looks like they're on it.
It's going to be in the GitHub. Yep.
Yeah, and I would just add on to there. This is.
Drive.
I would add on to what Will's saying there. This is your first chance to kind of look at, like, is my data coming out like I expect? Like, I set it up so that I'm measuring the X accelerometer there. Is that coming out as I expected there? And you could have already created for your axis conventions in your axis conventions file. Or if you haven't yet, this is a chance to kind of look at that. Like, oh, am I getting the axis conventions in the order that I thought I was? And this is the raw data before it's calibrated down to 1G. So it's just coming in that meters per second approximately at 9.8. And that's why it's okay that it's not perfect. It's just, it's good.
It's like there's a, which people are getting an error here where they're just getting nans instead of values for the A. So their calibration matrix isn't creating properly. Well, yeah, it will create a plot if there's only nans. So that's why that's happening. The question of why it's creating nans is another one.
So one thing to check, just to kind of do a little bit of error checking here, because we'll get used to this, is because everyone's using slightly different versions of the files, is you want to open up your data table and see that your data table has data in it. If you do, there's that, but then also the data file, the actual data table. Because what the Excel file is doing is it's matching up the times from your that you did the times here to the accelerometer data. So you want to make sure, this data table has accelerometer data in it. And if it didn't, then there's maybe it was a problem with the import or using the wrong file with that, and we can troubleshoot that issue. And if or make sure double check your bench test file, make sure that had the right times and stuff in it that would match up. So we can kind of troubleshoot what those are, but hopefully some people have gotten those working. I think for now, let's we'll just kind of keep going through, Will, and try to demonstrate what it should look like, and then we can troubleshoot individual errors later on.
Sounds great.
And the other question is that same mat file will have all of the information in it. We have it set up, the calibration, so you kind of click it on the mat.
So we're gonna get to that in the next step.
Go ahead.
Yep. So we've done the accelerometer position. So now I'm going to move on to cell 2. So now we're going to work through the gyro calibration. And like it says here, only run this if you have gyro data. If you don't have any gyro data, if your tag doesn't have gyroscopes, then don't worry about this. But ours does. So we're going to run this section. And it's going to once again ask for the mat file with gyro calibration. So as Dave was saying, the way this is set up is, say you created your accelerometer calibration on one file, and then you had to turn the tag off, and then you had to turn the tag back on and do your magnetometer calibration later, right? So now you have two different mat files that have this calibration data. It's not all just on one file. This essentially allows you to put in whichever file you need to be able to run this. So for ours though, we've gotten good at it so that we can sort of like do them all at once. So they all end up on one mat file. So we're essentially going to be asked to give the same mat file 3 times here. Once for the accelerometer, once for the gyroscope, and once for the magnetometer. So we're going to give this one again, and it's going to ask once again for this bench test file. We're going to get our frame rate. We're going to get our calibration matrix again. And now what's going to pop up this time is this figure here, which is essentially showing, figure will show, okay. So what this is, we have 6 different positions, and for each position we have 2 flavors of rotation, two rotation rates. So for position 1, we have the rotation rate at 33 RPM and then 45 RPM. And then the same for position 2, 3, 4, 5, 6. So each of these graphs, you can see in the little bottom right-hand corner of this graph, this figure is, this little subplot is for position 1, which would be, just main position of the tag, rotating at 33 RPM. And then the next one is position 1, rotating at 45 RPM. And what we're seeing here is the actual data for these gyroscopes. And what we're looking for is that these little peaks here, these red circles, actually align with the peaks of the data. So if these are sort of like offset, like say this little red circle was showing up in the middle of the sine wave, that would be something that would need to be corrected. And what we're seeing here is essentially that for each of these rotations, we have 2 axes that are rotating and 1 which is not. And so what's happening is we're essentially calibrating we're calibrating all 3, but the good thing to look at here is the axis that is not rotating. So what we want for that axis, so that axis is this third one up here, this purple line. We want this purple line to be fairly straight. And so if you zoom in enough, you're going to see that there's some squiggles. But in comparison, obviously, to the other ones, that's fairly level. And so that's kind of what we're looking for here. It's a plot that's got a lot going on in it. But that's kind of the main thing to look at. Dave, do you have any extra pieces to add in before we move on to the magnetometer?
No, I'm realizing a feedback I've gotten before too, which is to add labels to these graphs. So I will try to think about that as I go through there. So I know that's
cool.
Confusing.
Okay, so that's a overview of that guy. So that's calibrating the gyroscope, and so the sort of the final piece here, we're going to now move on to the magnetometer, and let's see. So we're going to run this. And again, we're going to input the same file, and it's going to ask us for this bench test calibration again. And now this time, we're actually going to have something to do. So it's going to open this up, and it's going to try to find the position, the location in the data that corresponds with what it thinks is when you are actually rotating your tag. And this section gives you a chance to sort of correct that a little bit and just sort of pinpoint where you want that to go. So in order to do that, this is going to pop up, and there's some directions on a lot of these figures as we're going through the PRH process. There's going to be some directions on each figure telling you what you should be clicking and when, and sort of how to go through it. And there's more data on that in the wiki. There's more tutorial on like how to click this, where to click, what you should be looking for. Again, obviously, if any of that's unclear, let us know. I'm happy to add more or update or change things for sure. So, but here, what I want to look at, this is probably fine, this whole period. But let's just say I want to cut out this little section in the middle here. It looks a little, I stopped rotating it for a second or something, so it's not working as well. So maybe I want to remove that section. So I'll click over here. I'm just left clicking, and then I'm going to left click maybe here. And if I press enter, it's going to change that box, and it's going to put that box in this new location. And once I'm happy with where I've put this, I'm just going to click enter again, and it's now going to move on to the next axis. So here, once again, I'm going to kind of like click here and maybe click there. and then click enter, and this new box is going to show up. There's a little visual glitch in here that we still need to fix, where the boxes from the previous ones keep showing up, but that's something on our list of things to just update in here. So I'm going to click enter again. Third axis, we're going to go here to maybe there, press enter. And now if I press enter again, we're going to see that all of this now comes up with all three of these laid out. So you can really see, you know, where you put your data. Does it line up? Does it fit? Does it look good? And I would say that looks pretty good. That I think is doing what we want it to do. Now, what's coming up here though is it apparently didn't find the field strength from our Excel sheet. So this is something that happens, and it'll come up with this warning, this error here saying go to this website and put in your location. So I'm gonna run that through for you guys right now. So we're gonna go here. We have the website. We have the website here. It's this NOAA.gov website. And you know, we can, if we know what our latitude and longitude is, we can, you know, type it in here, 36 dot, you know, whatever it is, and -121 I think is roughly where I am right now. Or you can just put in your zip code if you're in the US, or I think, yeah, it allows you to do city, state, zip code. So I'm going to do 93953. So it's going to add in that Latin long for me. So that's my position. And then I'm not going to worry about this start date and end date for right now. I'm just going to hit calculate. And it's going to come up with a bunch of numbers. But the important one here that we're looking at is this total field strength on this date. So what we're going to do is we're essentially going to take this. I'm going to copy that. I'm going to move back to MATLAB. I'm going to paste it. One thing I'm going to make sure I do, though, is remove this comma, because MATLAB doesn't like commas. And this is the actual number. It's 47,349.9 NT. I don't remember what that means. So I'm going to click here. I'm going to click enter. And it's going to input that for me. And it's going to give me back my data. And so what I'm looking for here, and this is on the top, it's for your magnetometer off, and on the bottom, it's for your magnetometer on. So again, for ours, it's the same, but for yours, if you do them at different times, they might be a little different. And so what you're looking for here is that the overall magnitude of your magnetometer, which is this black line, is above this red line here. So this red is sort of like your maximum that you're trying to hit. And yeah, that's in order to get a good calibration, you really want to make sure you have those maximum values in there, and that you're really seeing the maximum range of your magnetometer. And so if you're happy that you're getting that, you're seeing what you want to see. I think there's some chat here. Let's see. Okay, cool. Cool. Okay, so once you have that, and you know, let's say everything is looking good. Your accelerometer is good. You've set your magnetometer properly. Gyroscope is showing what you want it to be showing. You move on to the next step, and now this adds in a spherical calibration for both the magnetometer and the accelerometer. And let's see. So I'm going to run this section now. So this is kind of the big important one. So again, all of this is not real data. It's not really that important. But what we really want to focus on is this yellow portion here, which is the calibration period. So what I'm going to do here, I'm just going to zoom in on this, so you can see what this looks like. Okay. So what we're seeing on top, we have the uncalibrated, and on bottom we have the calibrated data. So what we're looking for is that some of this noise here that we're seeing is getting smoothed out, right? So we have a better line for our magnetometer, and that is what we're seeing. So all looks good. We can zoom out a little bit just to see, it's even really working on a lot of the data around that. So it's removing a lot of this variability here, which is good, because most of that variability is just noise that we don't really need. It's uncalibrated noise. And so once we're happy with that,
well, oh shoot, okay,
Dave.
Okay, I was gonna comment on that figure a little bit. Just to clarify that the difference between them is the cam off and the camera on period, so that they're, it's because sometimes the camera sometimes the camera has an effect on the magnetic field. And so that's why the difference is between the two graphs, but both of them are approximately equal to 1. And again, for the bench cals here, the point is to get like something fairly close to what we're looking for, the overall magnitude of the magnetic field. So that's pretty good for those periods. And then we'll do an in situ calibration to get closer to that. One of the questions that came up is, what were the declination values used? In this case, it doesn't actually matter, because we're looking for, as long as you did your calibration kind of close to that declination, to that magnetic north value, what that magnetic north value is, that's where you're getting those maximum values. And we're looking to just try to get to that maximum magnetic field. So we'll use the declination later to convert back to true north. But for these purposes, where we're just looking for the magnitude, the declination actually doesn't matter.
Cool. Okay, cool. So once we have gone through these segments, we're just going to go to section 5, which is where you actually save your calibration file. And we're going to run that section. Runs very quickly. Once that's done, you are all set to go. So now we have our calibration file here. So you can see it just created just now. So this is the file that later on today, even as we go through some of the PRHing steps, we're going to be asked to give the calibration file, and that's going to be this file here that we just created. So that's an important file to keep. We have like a list of all the calibration files for all of our different tags, and so whenever we deploy, if we deploy tag 55. Then we can go in and we can grab the calibration file for 55 and be good to go for that PRH. All right. So, okay, I think since we're good there, we can move along. Let's see, what do we, let's just get out of this for a second. So I think we're really ready to get into some of the PRHing stuff.
Yeah,
Really
and you guys are doing great. I know everyone's there's a lot going on. Let's just to kind of wrap up the calibrations a little bit, shake it off a little bit so we can see what we're doing at. So this is the cal file that Will just made. This is for tag 58, which we're going to be using just to kind of see some of the results of what comes in here, so we can kind of examine that. And again, like once you make your cal file, you don't have to worry about it too much. I know that some of this is like a little confusing too, and that we go back and forth between some of the old legacy versions of calibrations and newer versions of calibrations, and in situ versus bench cal. The procedure that Will outlined is just a pretty solid procedure to like make sure you have good data on your calibration data. And then we use some of these newer formats, the residuals that Will was showing there, and the axis values. Those are directly from the Tag Tools website that Stacy's going to talk about, and they're just newer ways to do the calibration. That's where the spinning came from that Will did. And so those are all good ways we keep track of those values in here, and there are these structures that are a little bit complicated to implement, but we've set it up now so you don't have to think about it too much as long as you have these cal files. The original values were these kind of calibrations and constant values, and these are just basically things you subtract from the data, and then things you multiply by the data to get down to the actual units that you want to use. So that's where these values kind of come from. And there's some implementations in scripts that we'll get to later on, including like apply cal, that will show you, that will kind of have the raw code. If you want to get into how you actually apply these calibrations, it'll get into some of these things, like how do you actually like subtract off the pressure calibration and add in these other values in there. So you can get into the raw code. So it is in there to look at those, of how you actually apply those calibrations to your data, but it's also kind of set up to do automatically once you create this calibration file. So cool. Depth sensor calibrations. Yeah, so Taylor's asking about depth sensor calibrations. That is that's a good question. If you have the opportunity to do a depth sensor calibration, that's awesome. You just like a pressure chamber or something like that. And then you would put that in. That's just basically this pcal and pconst, where pconst would be your subtraction values. Like what do you subtract off if you have a bunch of data? What would you subtract off that to get it down to be kind of oriented around 0? What is your intercept of your line essentially? And then you multiply that by your pcal. And we do it that way because instead of, it's not typically how you look at lines, but that is how you would do it. Usually you do the slope and then the intercept, but we do the intercept and then the slope because of how these matrix multiplications work, where you can then apply the matrix multiplication afterwards that takes into account the 3 axes and adjust for the axis orientation, which is why we keep these acal and such too, because they adjust for the axis orientations if you have axis orientations that are not aligned perfectly. That's how this will kind of adjust for those. But so you can add in your own pconst and pcal into this file, and that will help give you that initial calibration. And we'll also show you later on how to do an in situ calibration with the pressure cal using some of the scripts that Mark Johnson and Stacy have worked on, and Anne and others have worked on. Cool. Okay. If we're good, shake it off. We're gonna switch gears here again with the calibration. Any other last questions about calibrations before we move back to movie times? And we'll give you guys the kind of chance to be in breakout rooms and take a break if we need to here too. But we're gonna go back into movie times here in a second. So any other questions or comments about calibrations before we go on? Nice, thanks. Yeah, it's calibrations is always a fun time in the lab. It's a good way to get people using tag data and come up with this calibration file, that money cal file at the end. Okay, switching gears. We're gonna go back. We're back in we're back in the mode. We're gonna go back into, for the rest of the day, we're gonna start actually working in our workhorse script. We're back here. We finished this calibration script. We're gonna move into this inspecting frame times and movies. We're kind of gonna do this for the rest of the day and then start basically working on our main CATS PRH script. So basically the rest of today and tomorrow, we're gonna be working exclusively in this main CATS PRH tool script. So in your GitHub, there are a couple of, there's 3 main scripts, right? There's the calibrate CATS, which Will just went over. There is the import CATS, which we did this morning. And there's this main CATS PRH tool. So the rest of the time, we're gonna basically be working in this main CATS PRH tool, which is kind of like our envelope script that has all these other basic scripts in there to run these pieces. So you guys started using that last night with this make movie times. And I wanna just run this again briefly as a chance to kind of, for people who didn't get a chance to use this effectively last night. I wanna go over that one more time. And then we'll move on into actually inspecting those frame times files a little bit. Clear my workspace here, so we're back to scratch. So now all of my workspace is clear. We're all clear variables. And this is script number 1. This one does not rely on the import CATS data script, but after everything from 2 and on, we're gonna have to have our CSVs imported as well. So this is kind of importing the information from the movies. This is script 1 that you guys ran last night. And just as, so just to kind of show us where we're at, if just for those of you guys, I know a lot of people had success with this, but we'll just kind of go over it again just to kind of for what we have. So this is our raw data. One of the things that the script asks you for that people were getting confused on at the beginning is to select which files you actually want to import. And that's just because, again, data gets messy in the wild. And sometimes if your tag's floating for days and you have a lot of, or your tag comes off and you're just recording video of just the water, you don't actually want to import all that or spend, because you saw that this script takes a long time to run. And so if a lot of the data is not actually useful data, data, it gives you a chance to kind of say, I only want to import a little bit of that data into the file. And so one of the things that's useful is to kind of look at your data sometimes and be aware of what your data is. And so one of the things it's asking you for is, what is the first file on whale? So this one, I opened up the very first movie file, which is movie 2, because audio 1 is just an audio file. And the tag is on whale right off the get-go. So there's no time where like on the boat where it's recording data or anything like that I want to exclude. So it's starting right, it starts at audio 1 because tag 2, the tag's already on the whale. So that means file 1, the audio file that we can't see, actually it has data on whale as well. So when I select my first file, it's going to be this one. You want to also check the end of your files to kind of know like what's going on at the end of the data. Here's my last movie file. Is the tag still on the whale at this point? It is, but by the end of this file, it's fallen off. So this file I also want to include. I want to read this file because it has data on it. But if my tag had fallen off like here in video 13, and then it just recorded at the surface, then I might select this one as my last file, or 13 as my last file to import. So that's when it's asking you for those files at the beginning. That's what it's asking you for. It's also asking you for one more piece of information that was confusing people because I haven't introduced it yet. So that's on us. But in our example data, we've navigated now towards this towards our example data in here, right? But at the very outside, we use a structure called the tag guide to help us orient and organize our data. And if you haven't opened up this file yet, it's sitting here, and basically I highlighted in red all the really critical pieces that we'll actually pull from as part of this PRH process. So get used to kind of pointing the script towards this tag guide. And basically what it has is it has your ID here. And what the scripts are often pointed to do is to look for this ID, look up this ID in your table here, and then look for the tag on, tag off times to help it work better. So for instance, instead of me having to look through all of my video files every time to find when the tag came on and off, if I know this already because I ran that import cats data and was able to see where my tag comes on and off, I can have that information in here and it'll automatically select what videos and audio to import. The recover time is important because those audio files that are sitting as your tag is floating in the water, that might actually be useful information. Like if the video is not doing anything useful, you don't need to like sync that with the data, but you might want those WAV files because your tag is actually essentially a floating hydrophone. So if you're interested in acoustics and like what sounds are whales making, you might want that. So it pulls this recovery time out of the data as well to know like, okay, how much of that audio do I want to actually make WAV files from? So it uses that. So if you don't want to select those automatically, it gives you the chance to select that tag guide. So when you run this file, when you run this first script here, these again, so just as to kind of orient yourself to how these run, there's a bunch of basic information here. Here's the information about making those WAV file directory in our WAV files, running that FFmpeg that Will showed us yesterday. So you have those WAV files from the video files in your raw data file folder. When you run this script, most of these are setups you won't have to change them, but you can change this to give it a directory to start looking at it if you want. If you don't set that correctly, then you're just gonna have to find it, but it just makes things easier over time. You can also, like, based on how your data looks, you can set some different parameters here, and based on how old your data is, you can set some different parameters here as well. This time warning is basically looking at like, okay, what's my margin of error for how close the video, how many frames off of video data can be from the accelerometer data. And we usually set that as 0.1 because we usually decimate our data to 10 Hertz. And so anything less than that, we're like, okay, that's closer than our data is measured to anyways. So we don't need to worry if there's a 1 or 2 frames different because that'll be a 30th of a second. There's about 30 frames per second. So I set that there. And if you only decimate, if you're only in the habit of decimating your data to 5 Hertz, then you might be put 0.2 in there because then anything closer than that is going to be good for you. Or if you want it to be super precise, you can decrease that value as well. So that's what that is. And so when you run this section and you navigate to your folder here, I'm just going to copy that folder and navigate to my folder with my data here. And it's asking me here to select the first movie or audio file from the deployment. So that's the first thing I check on. We know that the video 2 is on the whale. So audio 1 is also going to be on the whale. So I'm going to select that one. And then it's asking you for the bin file. That's just giving you the name of the file. And then the reason it kind of kept going, there's automatically found that tag guide, that it's importing that tag guide automatically to work with that. Other people have had to actually ask you to select for the tag guide, and you can find that tag guide and select it, or you click cancel, and then it'll give you a chance to find that first and last audio and video files. So if anyone had any problems with that, you can let me know if that doesn't make sense. I know it automatically found it for me, so I can't show you to it right now, but that's the first thing. Okay, I'm going to pause this. I can. Sometimes it doesn't love pausing in the middle of these things. Okay, so clear this. And then I want to skip to running that. And so the resulting file in our workshop file in this Antarctic, if you weren't able to run that movie times file and get the resulting file, we put it in here for you. So this movie times file and this audio data are scripts that should have come out of our workshop file. So I'm going to now put them into my raw file here. So you should have been able to create those. And so if you download this data now, again, it has that data in there. And the movie times file is this piece that now has this variable called frame times in there. You show what the graph you get looks like. Question, can I show what the graph you get looks like? Oh, at the end. Yeah. Yes, I can. I didn't save that. So at the very end of the file, it'll create a graph. Yeah, sorry, shoot. I should have, I'll try to look for that. That's a good question. So at the very end of this movie times, you get a file that basically looks like a lot of lines that is basically giving you the timestamps of every video frame, and you should see some gaps in there. That's a great question. I'll try to run this again tonight and save that graph so I can show you what it looks like. It will approximately look like this. So in the wiki, there's an approximation of this idea. It's slightly different than this now, but it approximately will look like this, where you have a frame number here on the x-axis and time on the y-axis, and it'll basically look like a series of lines that's showing you these pieces, and then it has a number here that says the video number of the video, and it will have red X's if you have errors, if there's like a spot where there's a big jump in the data or something like that. If not, then it should look pretty just like this. And there might be a gap in the data between where there's a jump in the video time, where one video ends and then there's just a dark period where it's recording audio, and then the next video starts in a little time. So you might see a jump between one video 5 and video 6. So that is what that example would look like. And I'll try to run that and show you the exact example. But one of the things, the output of this is this frame times file. And so what we're going to do for the next most of the rest of the time today, before we kind of jump into like using this main CATS PRH in the next section here, is looking at exploring what this frame times is and why we actually make this file. So it's kind of the last thing we're going to do, where I just want you to kind of like understand why we're doing what we're doing and why we're kind of getting into here. Because if you come up with errors on your own, I want you to understand at least what it's trying to do and why it's doing this. So for the next about half an hour, and then we'll come back at 12:50. We're gonna go back and do this activity from the workshop folder. So in my workshop folder, in the workshop materials, there is a day one. We're gonna go back to day one. We're supposed to do this yesterday. In the day one, there is this Word document that kind of helps you explore both the video and understanding how CATS videos work specifically, and also that frame times data file and what that frame times does. So you're going to need that frame times, that movie times file that you either made or the one that I just put up in the folder there, and this Word document. And that will help you describe what, kind of look through that. And we'll just send you out to breakout rooms again to kind of look through that document and work on that. And I'll be available for questions. I'm happy to jump in and out of some breakout rooms to help you guys think through that. But spend some time just basically kind of going through step by step here and seeing if you can explore this data and go through and like actually look at these video files a little bit. So you're going to need some of the video files from the raw data and this frame times movie files. Yeah. So we'll go with that. Does that make sense? Are there any questions about that? Yeah, it's just so to be clear, the movie times file and the audio data should when you run the file, it should create them automatically in your kind of external. So right next to your raw file, wherever your raw data was stored. Outside of that, because we try to keep just the raw data from the tag in the raw folder. Everything else we try to start creating in here. So it should create that movie times and that audio data in that folder. Okay, Great. I'm going to send you guys back to the breakout rooms we had earlier today, and I'd like you to just spend the next about half an hour trying to run through this part one movie times document to see if you can actually look at these frame times and explore and use a little bit of MATLAB at this to have this understanding of what these frame times are. Okay, I'm going to send you to breakout rooms. I'm going to stop sharing my screen. And then we're going to send it out over there. Cool. And then we'll come back at the end and look at back to that main CATS PRH again. So I think you'll have to select to join on your own, but should be able to do that. And those of you guys who were not earlier, I'm just going to assign you to rooms, and obviously feel free what makes sense. You. Cool. And I'm going to stop the recording. Pause it for now. Sweet. Everyone's popping back in there. Hopefully we're able to look at the video times a little bit. People are repopulating here. Got some reports that people are having some issues with the Google Drive and functionality and being able to download files effectively. I apologize for that. We're trying to make it dynamic, and so things keep changing, but it means that there's a lot of downloading, and I know that can be frustrating. One sounds like some folks were able to use the Google Drive file stream. Then you still might have to copy then at least you have an updated version of everything, and it's not getting messed up in the zip process. But you still might have to copy everything over to a hard drive because you don't have write privileges on the Google Drive because they're shared. So we want everyone to be able to have the regular pieces. So I can, it's like the critical thing is to be able to have this this example data folder is of course the big one that has all of the CATS raw data in there, and that should mostly be fairly static or be able to just draw one or two files from it over the next few days as we add and make adjustments to the infill file that is creating our PRH file, and which most of it we're going to run through tomorrow. Basically going to have just an all day running cell section tomorrow to be able to run through these files. So if you have this example data downloaded for tomorrow, that'll be the critical thing, and we'll have in there all of the critical pieces are in there. So if you even if you start over again and just have it all downloaded for tomorrow, that'll be good. The piece that we're going to have you create tonight still is this the mat file for this the raw data. So it's basically running your import CATS data that we did earlier on this raw example data, and it's here if you're not able to do it. But if you can run it tonight, that'd be good. I realized I've got all the reports. You guys were saying, oh, there's a warning coming up for the 2020 import CATS data. Turns out that warning meant something. So you guys were not wrong to be warned by the warning. And that's, I think, that explains why people are having the issue with the calibrate CATS when you've got all the NANDs. It's because the timestamps weren't lining up. Because in the 2020, what it's reading is it's for some reason it freaks out at the date times that in the format it doesn't recognize and just imports your system time. And so it's giving you a wrong timestamp. So I will work on that. I'll fix that. I'll try to have an update for you by the 2 o'clock session today. And then you should be able to run that import CATS data. For anyone using older than 2020 or after I update this one, the goal tonight is to be able to just run essentially just as we showed earlier, be able to run this data equals import cats data on that example file. So download that example data, step 1, run import cats data, step 2, and then you will be set up for tomorrow to start. Tomorrow, we're going to plow through the main cats PRH tool, and most of that is just going to be in the main session, and we're going to be going through, and we're going to, by the end of the day, we're going to have essentially a PRH file with some I want to show you this to get you jazzed, or actually we have it in the example folder. We have a quick look folder, and basically by the end of the day, we want to be able to make this kind of folder that has our track for the whale and our some images. So basically we have this quick look to be able to look through and say like, well, what is our whale going to be doing? We'll share some pictures. I know if those of you guys who've been looking at the videos, you're like, where is that tag on the whale that it looks so funny? Well, it's because this tag is really far back on the whale. We'll basically be able to create this quick look that has this information about the depth profile, the pitch, roll, and heading of the animal, and this track of the animal tomorrow. So that's where we're going to start tonight. Run the import cats data and get that going. If you guys are having any thoughts or questions or having any problems with the import cats data, we will be around this afternoon, and we'll be available to answer questions. I'm trying to see the chat here in a second. I know there's some questions coming in. Where did it go? Stop the share. Okay. 2019 and got NANS. Okay, so we'll look NANS issue in 2019 as well. Okay, so I'll try to run some tests on those import cats data for those that file and see if we can figure out what's going on, why people are getting weird timestamps that are not being read correctly. Yeah. All right, we'll take a look at that. I'll try to run that and see if anything's going on, and if anyone has any ideas, let me know. I'll try to have that update for you guys by the 2 o'clock session, and we'll go from there. Other than that, thank you guys for your time today. I want to, if you have a time before you go, please, we do really appreciate the feedback on the session. So I'm going to send you guys another link right now. It's really helpful for us to have this, the feedback on what's going well and what's not going well. Oops. Send to everyone.
Dave, and one thing, if we put the link in here, anybody who's working on the Zoom online won't be able to see the poll. So we might want to send it out somewhere else as well.
Yeah. Sorry. Yeah, there is some. I know the polls haven't been going for everyone online. Hopefully, everyone can see the chat link though for this Google Forms. So check that out. There's some other questions in the chat. I'll stick around and answer any of these questions if anyone wants to. Other than that, please fill out that form and we'll wrap it up for the day. Yeah, that's what we'll do. Let me see what these questions say. All right, my code finished running for the calibration and creating a plot. 1 row of NANS. Uh-oh. Okay, yeah. So yeah, if you're getting warnings on the calibration file about a median of 1.5, that's probably off, probably because you had a column of NANS. So we can try to figure out why that's not imported correctly. And then the movie times file didn't work. Okay, so yeah, if anyone had problems with the movie times file, there is the backup file online. So we'll take a look at these. Please fill out the form if you get a chance, and we'll be here at 2 o'clock if you guys want to come back for like any brainstorming sessions or anything, and I'll work on that, updating the import cats for the calibration files that I know people are having issues with. Other than that, we'll start in the morning, and by the end of the day, we'll have some pretty sweet data to look at. So good stuff, guys. Thanks for your time.